This is the final part of the 17th lesson in heat transfer. In the 17th lesson, we have been developing a qualitative picture of convection heat transfer. This qualitative picture will be the foundation upon which we will interpret correlations used for calculating convection heat transfer coefficients in a variety of flow situations. In the final part of this lesson, we will be looking at one of the most important dimensionless numbers in convection heat transfer, the Nusselt number. By the end of this lesson, you should be able to recognize the definition of the Nusselt number. You should be able to explain what the variables in the Nusselt number mean physically. And you should be able to explain why the Nusselt number is so important in convection heat transfer. On with the lesson.
So then, what do the equations ultimately look like? So you're not going to see equations for H directly, because just like we have a non-dimensional number for the hydrodynamic bond layer thickness, the Reynolds number, a non-dimensional number for the relative thicknesses of the hydrodynamic and thermal boundary layers, that's the Reynolds number. We're also going to have a non-dimensional number for the convection coefficient. That's called the Nusselt number. Okay, so it's another dimensionless number. I want to try to give you a sense of where it comes from, this Nusselt number. The Nusselt number is actually a non-dimensionalization of this equation that we started the whole discussion of convection heat transfer with, over Ts minus T infinity. So this is a dimensional equation, we're gonna non-dimensionalize it by defining two new non-dimensional variables. We're gonna define a non-dimensional temperature as T minus, so the temperature relative to the surface temperature, over the free stream temperature relative to the surface temperature. And we're going to find a non-dimensional positional coordinate as the positional coordinate y that we've been thinking of relative to some characteristic length scale of the problem. What that characteristic length scale is depends on what the problem is, okay? And you'll know from the definitions, so don't panic too much about what that is, that L sub c, okay? Just think of it as a length right now. So what I want to do is I want to take these definitions and solve them for T, and then put those into this equation over here. So what I have is T is like the dimensionless temperature T star times T infinity minus Ts plus Ts, yeah? And the dimensional positional coordinate y is the non-dimensional positional coordinate y star times the characteristic length. So if I take those and I substitute them in to this equation for the convection heat transfer coefficient, right? In the numerator, I have minus kf times, I'm going to leave the derivative up here. So it's like the derivative of t, which is now like the dt star of t infinity minus ts plus Ts, right? And what I have in the denominator is that Ts minus T infinity, and I have the dy term. So now I have a d times my substitution for y star LC. That derivative is at y equals 0, but where y equals 0, y star equals 0, right? That's still, y star represents the fluid solid interface. So now if we take the derivative, right, and we apply what we know to be true about calculus, this is like the derivative of the first term plus the derivative of the second term. The derivative of the second term is like a derivative of a constant because the surface temperature is just one number in the problem. So that goes away. And what we're left over with is the derivative of the first term, and the T infinity minus Ts is a constant and can get pulled out of the derivative, right? It gets factored right out. So in the numerator now I have minus Kf times T infinity minus Ts times what was left over, which was the dt star. In the denominator, I have Ts minus T infinity. And then same idea here, the y star is It's going to vary, but the L sub C is just a single number, so it can get pulled out. So D Y star, where? At the fluid solid interface. Now notice if I take this minus and I factor it in here, I can flip the TS and T minus T infinity, and that just ends up canceling, that goes away. And now what I'm going to do is I'm going to take what's left over, the L sub C and the thermal conductivity, and I'm going to lump it together with the convection heat transfer coefficient. And what I have left over is a non-dimensional or a dimensionless, same way of saying non-dimensional, temperature gradient at the fluid solid interface, right? This is the Nusselt number. This is how the Nusselt number is defined. It's H times some characteristic length scale over the fluid thermal conductivity. And it represents a dimensionless temperature gradient at the fluid solid interface. It's kind of where it comes from. So the Nusselt number is sort of says something about what this temperature gradient is. Okay, so this is the critical thing to have right here. We go till 12:20, right? Or are we already done? I get confused.
It's 12:20.
12, okay. So one thing to write down about the Nusselt number, when the Nusselt number is equal to 1, this is like pure conduction. Because I can try to convince you that this really represents like a pure conduction case relative to a case that's enhanced by advection. So the Nusselt number should never be less than 1. If you ever calculate a Nusselt number and it's less than 1, you've made a mistake. Because we anticipate that the advection is going to enhance the heat transfer, right? It's going to make the gradient steeper than what it would be if it were conduction, only conduction. So whenever the Nusselt number is greater than 1, we have advection enhances the heat transfer. So this Nusselt number has, you should think of it as the Nusselt number has the convection heat transfer coefficient in it, which is what we want, right? We want H. But notice that it also includes the fluid thermal conductivity. So if I want to calculate H, I take the Nusselt number and I multiply by the fluid thermal conductivity divided by whatever the characteristic length scale is for the problem. So like for these plates, it will be the plate length.